Okay, more Faraday's Law practice problems. I think I actually may post this one first, even though I recorded it last because it's the easiest example that we're doing. So this is problem 6 from the chapter. A 10.8 centimeter diameter wire coil is initially oriented so that its plane is perpendicular to a magnetic field of 0.68 teslas pointing up. During the course of 0.16 seconds, the field is changed to 1.25 teslas pointing down. What is the average induced EMF in the coil? So we've got a situation where you've got a magnetic field that starts with one value, and that magnetic field's value is changed. It doesn't say at a constant rate, but I think you're supposed to assume that it's at a constant rate. If not, and that's the reason why they say the average EMF instead of the EMF. So we've got a magnetic field. This is what chapter in 29-6 problem. You got a magnetic field pointing up. I'll draw it out of the page. Out, 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 out. B initial is equal to 0.68, I believe it was, teslas. 0.68 teslas. And that magnetic field is going to gradually decrease and then point the opposite direction. So B final is equal to 0.25 teslas down. We'll put a negative sign. So at the end of the situation, the magnetic field will be pointing into the page. That means the change in magnetic field is going to be equal to 0.68 plus 25, or 0.68 minus 0.25. So 0.68 plus 0.25 is equal to minus 0.93 teslas. And the rate of change of the magnetic field is just going to be equal to delta B over delta T. Again, we're going to assume that this change is constant, so that's minus 0.93 teslas over the time it says that this occurs is 0.16 seconds. So delta T is 0.16 seconds. So dB dt is equal to minus 0.93 over 0.16. I get 5.8 teslas per second. We're asked for the EMF through a loop. The loop in the magnetic field has got a diameter of, what was it, 10.8 centimeters. So the radius of that loop is equal to 5.4 centimeters, or 0.054 meters. The EMF through our loop by Faraday's law is minus the rate of change of the magnetic flux. And the rate of change of the magnetic flux is just going to be d dt of B times the area. The magnetic field and the area are perpendicular to one another. The area isn't changing, so we don't have to worry about any dot products or sine thetas or anything. And the rate of change of B times A, since the area is constant, is just A times dB dt. Okay, so the EMF generated in this loop is going to be equal to the area of the loop, which is pi r squared, times the rate of change of the magnetic field, which in this case is minus 5.8 teslas per second. And we'll take care of we'll talk about the direction. We'll take care of all the signs ourselves. So let's see if we get the right answer here. 3.14 is pi times 0.54 squared times 5.8. I get the magnitude is 0.053 volts. Real quick, check my solutions guide, which I have open in another window. Where is that? 5.3 times 10 to the negative 2 volts. Yes, okay, so that's the right number. What's the direction of the EMF and the induced current in the loop? If the magnetic field is pointing up initially and is decreasing until it's pointing down, the induced EMF in the loop of wire is going to oppose that decrease by creating its own magnetic field pointing up. And the way it does that is with a current in this direction. So the EMF and the current will push charges around the loop that way. Okay, so yeah, we'll go ahead and I'll assign a few more straightforward Faraday's law problems. There probably won't be a quantitative Faraday's law problem on the final exam, but there likely will be some qualitative Lenz's law problems and problems where you are asked to explain what will happen in a certain situation in terms of magnetic induction and understanding the direction of induced currents due to changes in magnetic flux.